Hey guys, Dr. Brown here, and tonight we're looking at moments and centroids. So let's get after it. Don't freak out. I worked this problem out just so we wouldn't have a video that's 2 hours long. So, alright, our goal here is to find the moments about x, the moments about y, and then the centroid x bar and y bar. And we're given that x equals y plus 2 and x equals y squared. Now you'll notice immediately that they didn't give us y equals f of x. It's x equals f of y. Now you could change it, but I'm a grapher, okay? I love to graph things because I'm dyslexic and it allows me to see what's happening. I would encourage you get comfortable graphing because it tells you a lot, especially in this one. Okay, so what I did first, I set these two equations equal to each other to see when they're touching. So I subtracted y and 2 from both sides, and then I had y squared minus y minus 2. Then I factored the y squared into y times y, the negative 2 times 1, but I didn't know I had to 2 times 1 or negative 2 times 1 or positive 2 times negative 1. If I add those together, it needed to give me a negative y. Okay, it needed to give me this term. So I knew I had to have a negative 2 and a positive 1. So now cross multiply, negative 2 times y is negative 2y, positive 1 times y is positive y. Add those together, it gave me the negative y. Negative 2 times positive 1 is a negative 2. Y times y is y squared. So now I have y minus 2 times y plus 1, and those equal 0. So y equals 2, y equals negative 1. And that's where the two curves touch. Okay, so I could, from that point, have looked at x-intercept and y-intercept of each curve. I could do that, but what I did was just made a simple graph, and I put my x's to the left, the y to the right. That's just good housekeeping, I think, because when you go to graph the thing, you're always looking at x's, x in a parentheses, x, y. So I label it that way. So, all right, I put my x plus 2 here, and then y squared here for y. And I started at negative 1, went all the way up to 2. Because we're looking for the area that's bound by this and what that area is doing. Oh, and I should say it's a uniform density throughout this planar region. Okay. All right, so when y is negative 1, y squared obviously is 1. We'll just work through that one. So 0 squared is 0, 1 squared is 1, 2 squared is 4. Okay, so now negative 1 plus 2 gives me 1. 0 plus 2 is 2. 1 plus 2 is 3. 2 plus 2 is 4. So then I just graph those. So I have 1, negative 1. So x is 1, negative 1. That's that point. So I'll just go through this one. Then I had 0, 0. That's this point here. 1, 1. So x is 1, y is 1. Then 4, 2. 1, 2, 3, 4, 1, 2. That's this point. So that allowed me to say, okay, that's my y squared term. Now obviously, if I had other terms, other values, it would go on out here and go over there. But we're looking at the area bound by those two curves. All right, this one, 0.11, 1, negative 1, so 1, negative 1, and they both, you can see both of those touch. Then the 0.20, so 1, 2, 0, 3, 1, 3, 1, 4, 2, 4, 2, that's this point. So that's just a straight line. Now, if we're looking for the area under the curve, if I were, and I like to do this in terms of we get comfortable differentiating with x, something dx. Hey, we like that. And most books have a ton of problems, some function dx, dx, dx. And then when we get to something where we need to use a dy, we're, you know, it's just not comfortable. So this problem, if you think about a dy, and we want to get the area, if this were f of x minus g of x dx, f of x, g of x, you know, for a given value of x, what's the larger y value? And that becomes your f of x, so it'd be this term. Of course, in this case, let me flip around here, we would have, if we solve for y equals x minus 2, and y equals plus or minus square root x. So now this term here would be plus square root x. From here to here is minus square root x. And then this term right here is x minus 2, this line from. So if I'm integrating, trying to find the area, and I'm integrating with respect to x, I would have two regions. I have two integrals I have to work with. This would be, f of x would be plus square root of x minus square root of x. So now I have the integral of 2 times square root x dx. Okay. Now you can do that, but simplifying it, let's just integrate with respect to y. So for a given y, what is the larger x? And that becomes your f of y equation. So we can see this line provides me the larger x value than this line for a given y value. So I'd have this value of x or that value of x. So this becomes f of y. The y plus 2 is f of y. G of y then is the y squared term. All right, we okay with that? Make certain my mic is still rolling. Okay, so let's integrate that. We're going to integrate that from -1 to 2 on the y-axis here. So we have the f of y was y plus 2 minus y squared, which was g of y. So we go through the integration of that. We end up with the area is 9 over 2. So that would be in square units. Now we're trying to find the moment about x and y. What is a moment? It's a mass times some distance. And if I have the density, so now I have mass per unit area times area gives me mass. Okay, times a distance. Now that distance is to the axis that's in question. Okay, so in our case we're looking at the moment about x. Well, that's the integral of the area, which is rho times the, it's the mass, it's rho times the area. We just calculated area here, see? So it's that same formulation, rho times area times the distance our little differential rectangle is from the x-axis. So if I'm looking at the center of that thing, how far is that from the x-axis? It's y distance. So now, so my mass times the distance integrated on y. So let's go through that. So I have the integral, rho times the integral from -1 to 2 of y plus 2. That was my f of y here. Minus y squared times y. So if I multiply through, I have y times y squared plus 2y minus y cubed So now I integrate that, rho times that integral, and my limits were -1 to 2. So if I walk through all of that, I end up with my moment about x is 9 rho over 4. Don't laugh at my rho symbol. It's not too snazzy. All right, let's repeat this with the moment about y. Again, it's the integral from c to d of the mass, which is rho times the area times the distance, and now it's the distance to the y-axis. So I have the rho times the area, the f of y minus g of y. Now, what's the distance to the y-axis? So here we are. It's this x value here and this x value here. Well, since we're integrating with respect to y, now it's going to be f of y, then we're talking about a given y here. So given y, f of y plus g of y divided by 2 would give me that point right here. Instead of looking at these, I'm getting the average of that. Now if you take the 1/2 to the outside, so here it is, 1/2 times rho, and you FOIL this thing out, you have f of y squared minus f of y g of y plus f of y g of y, which those two cancel, minus g of y squared. So f of y squared minus g of y squared, integrating that from -1 to 2 with respect to y, and of course I have my 1/2 rho on the outside. So again, f of y we said earlier was y plus 2, that's squared, minus g of y squared, don't get hung up on that, okay? Now if you work through that and integrate, so all I did was FOIL this, and then that's to the 4th power. So now y squared, if I integrate, it's y cubed over 3 plus 4y squared over 2, that 4 over 2 reduces to a 2, plus 4y minus y to the 5th over 5 from -1 to 2. Okay, if we walk through the math on that, we end up with the moment about y is 36 rho over 5. Hey, hang with me, we're almost there. Now, x bar is the moment about y divided by the mass. So the moment about y divided by rho times the area. So I had the moment about y was 36 rho over 5 divided by rho times the area, and the area was 9 over 2. So that gives me, if you just go through the algebra there, x bar equals 8 over 5. So now my y bar is the moment about x divided by the mass, the moment about x divided by rho times the area. So the moment about x was 9 rho over 4. So 9 rho over 4 divided by the area, rho times the area. So that ends up, work through the math, y bar equals 1/2. So in summary, what we have is the moment about x is 9 rho over 4. Moment about y is 36 rho over 5. The point of the centroid is 8 over 5 was the x value, and 1/2 is the y value. Now, if you integrate this on x, these formulas, you'll have to redevelop those. As a matter of fact, in most every textbook I looked through recently, they had them all in terms of dx. And then the author was sneaky. He started giving you problems with respect to y, just like this one here. This is a good one for your teachers to stumble you up on an exam, so be careful with that. Okay, so what did that mean when we were looking at what function is f of y? We're looking at, for a given y, which one has the larger x, which function. In this case, it was this one. Just like when we're looking at which is f of x, we're looking for which one has the largest, for a given x, which function has the larger y value. So now it's for a given x, or for a given y, excuse me, for a given y, which is the larger x, and that becomes f of y, this is g of y, which is not intuitively obvious because we're always integrating with respect to x. Okay, I apologize for all the bad writing here. I'm not the most, my penmanship's not really that good. Okay, why are we doing this? Hey, together we're trying to build a better tomorrow and do that through math. Try to find as many moment and centroid problems. You guys at TSU, keep working them, and we'll try to help you as best we can. Okay, that's all for now. We'll talk to you next time. Thanks.